Alrighty, this next video that I want to do is going to be on our partial derivatives and all the stuff that we've been learning, and hopefully I can get a couple of minutes to go past what we've learned so far so that you have something to look forward to. Cool. So we've been talking about functions of multiple variables. Typically we just have functions of x, but now we're going to functions of x and y. Our standard derivatives for functions of x we called d by dx, or sometimes f prime. But we need to be able to generalize this to something else. So d by dx instead becomes a partial with respect to x, or a partial with respect to y. We'll see what this means and what kind of rules we get from this. But so far, nothing out of the ordinary. We're just writing the d as a curly d now. Funnily enough, that's just what we call it. We don't call it anything else. We call it curly d. Here, the notation for prime is kind of similar, but instead we write a lowercase x, or if it's with respect to y, a lowercase y. Cool. The reason I group these together, this is our Leibniz notation, this is our Newton notation. So this was invented by Leibniz, I think his first name was Gottfried, and this was Isaac Newton's notation. They're thought to invent calculus around the same time, we're not entirely sure. But we do get new notations for it, and these notations can be useful in different situations. So what does it mean to take a partial derivative? For the regular derivative, say we had a function that looked like 4x squared plus 2x minus 7. Our standard derivative rules tells us that we can bring that 2 down, so we get 2 times 4, which is 8, x, and then 2 minus 1 is 1, so don't worry about it. Plus, the 2 times x just becomes 2, and the derivative of a constant is always 0. So this would be our f prime of x. But what if instead we had a function in several variables? So what if we had f of x y equals 8x squared y plus 2xy plus 3x plus y minus 7. It's a bit long, but it kind of gets the idea across pretty well. Then we want to be able to take a partial derivative, a derivative just with respect to x or just with respect to y. So the idea that mathematicians came up with is why don't we just treat the non-differentiable variable as a constant, or we're just holding it still while we measure the rate of change in the other direction. So that gives us that the derivative with respect to x, I can take and I can break apart the derivative just like I would this regular derivative here. So that's the same thing as the derivative with respect to x of this first term, 8x squared y, plus the second term, the derivative with respect to x of the third term, the derivative with respect to x of the fourth term, and the derivative with respect to x of the last term. The minus sign there. Cool. Now, one of the rules that we get for partial derivatives is that the partial with respect to a variable of a function that is in the other variable is 0. It doesn't make sense to say that I'm taking the derivative in one direction of a variable that's not in that direction, right? That variable, y, has 0 component in the x direction, right? If we think about the graph, this is y and this is x. Y goes nowhere in the x direction. It has 0 component in the x direction. So this is always 0. That tells us that a couple of these go to 0. This one specifically goes to 0. The partial of x with respect to, or the partial of y with respect to x goes to 0. Similarly, constants always go to 0. It doesn't matter if we're taking them with respect to a variable or another variable, it always goes to 0. Cool. Another thing is we're treating these as constant. So it's like multiplying x by something. With a typical derivative, if we're multiplying x by something, we can just take it outside the derivative, and the same is true here. This gives us, we can bring this 8 and this y outside. So we can bring this 8y out, and we're left with just the x squared. Likewise, we can bring this 2y out, and left with just x. And here we can bring the 3 out, and we're left with just the x. Another interesting rule that we get with partial derivatives is that the partial derivative with respect to a variable of a function that's only in that variable is the same as the regular derivative. So here, all these partials of just x's behave normally. They behave like a regular derivative. So this means we have 8y is still outside. The derivative of x squared is 2x. This 2y stays outside. The derivative of x is 1. This 3 stays outside, and the derivative of x is 1 again. We can simplify this, and we simplify it with the standard that we put numbers first and then ascending alphabetically. So like x, then y, then z if we had it. So this is 8 times 2 is 16, x, and then y. 2y times 1 is just 2y, and then 3 times 1 is just 3. So this would be the partial derivative with respect to x of this function. Now we want to go through, we want to find the partial derivative with respect to y of this function. And we can do it the exact same way we did the partial with respect to x, but instead we're doing it with y. So we can break it apart, pull the non-y stuff out now, and then do our standard derivatives. So the partial with respect to y is the partial with respect to y of these individual terms. Cool. So again, all I've done is I've written the partial of each individual term. Then I can pull out all of the non-y stuff. One thing that I note though is that forces 2 of my derivatives go to 0. This goes to 0, and this goes to 0. This is the derivative of a constant, so we get nothing. This is the derivative of only x, only a function of x, so we get 0. Cool. I can pull out the non-y stuff. So this is 8x squared partial with respect to y of y, plus this 2x can come out, partial with respect to y of y. Nothing can come out here because it's just the partial with respect to y of y. Cool. Then I can differentiate normally. This is going to be 8x squared times the partial with respect to y of y is 1, so times 1, plus 2x also times 1, plus 1. Cool. So this gives me 8x squared plus 2x plus 1. And that's my partial with respect to y of this function. So now we've seen how to take a partial with respect to y and a partial with respect to x. And that's how you do your first order partial derivatives.